So now problem 6. One molecule of the product C is formed from one molecule of the reactant A and one molecule of the reactant B. The initial concentrations of A and B have common value. So that bracket A stands for concentration of A and bracket B is concentration of B. It is some A moles per liter. Then the concentration of C is the product you get, is given by this function where K is a constant. Question is, find the rate of reaction at time t. Rate of reaction is the derivative of the concentration of the product. Alright, so if capital C, bracket C is this function, you are going to find the derivative of this concentration with respect to time. So t is the variable here. So look, there is a t upstairs and downstairs. So you're looking for quotient rule. Denominator square, derivative of the numerator, denominator as it is, minus numerator as it is, derivative of the denominator. Okay, t is my variable. So when you simplify it out, notice this distributes minus, this is simple multiplication, a cubed. So this term and this term is identical, but there's a subtraction, they cancel, so that's what you're left with. So let's type that in. So it's a numerator over denominator. Okay, so write the parentheses first, then a to the power 2k, there's a numerator, and akt plus 1 power 2. That's a part. If x is concentration of C, what is dx dt in terms of a, k and x? So notice they want dx dt without t. So if x is concentration C, then x can be written as this function. Alright. So look, you don't want your answer to contain t. So let's take care of t, that is solve for t. Cross multiply, you get x times this equals a squared kt. Alright, x has denominator of 1, so 1 times a squared kt. Distribute the x, right hand side is fine as it is. Get the t term to the left, this minus this equals, move the x to the other term here. So if I can factor out a t, so I need to factor out a t, so I should write the t there, right. So I factor out the t there and divide out by this factor. T is negative all of this, okay. So notice here, a is common, k is common, that's what I did. X over negative x over ak, x minus a, so fine. Now dx by dt is what I need to know. So dx by dt is the derivative. We just saw the derivative. That's all I have written. But I don't want any t in my expression for dx dt. So I replace that t by this expression in x. Alright. So once I write it down, so that ak cancels that ak, I'm left with negative x over x minus a plus 1. Everything else is fine. The t is gone. I'm simplifying it. 1 is nothing but x minus a factor over x minus b. The reason I do this is because I'm going to add common factors. Once I resolve this, I continue to resolve it. Okay, so look, there is a square. When I divide by a fraction, denominator goes up and that square applies. Downstairs, x's cancel, I'm left with a, negative a alone, but squaring it gets me positive a squared. That cancels this. So all I have is K times X minus A quantity squared. All right. What happens to the rate of reaction? Rate of reaction as T goes to infinity. Rate of reaction. So there, that's the rate of reaction. As time goes to infinity, right, as time goes to infinity, this denominator has T, so that goes to infinity, so the fraction actually goes to 0. D, what happens? Oh, I'm sorry. Rate of reaction is D, so that's what is 0. Now, C says what happens to the concentration as T approaches 0. Concentration itself, that's C. So that's concentration. Now, as T approaches 0, okay, let's understand that. As T approaches infinity, what happens to C? C approaches, you may know this, T and T, so only those coefficients survive, approaches A squared K over AK. So all that cancels except for an A. So you're going to get A. All right. Oh, it's lost connection, but trust me, this is correct. Okay, so it's taking time, so I'll stop here with this problem.